Okay, thank you very much for the introduction. Okay, so I want to tell you about a problem in semi-supervised learning. So the problem we have is that we're given some data set xn, so these are points in Rd, so xi from 1 to n, and we're given a subset of labels. So the labels are indexed by this Zn, which is a subset of 1 to n, and we're really thinking of working in the regime where this set is very small. So in particular, this little n we can think of as being very, very big, and the size of this set Zn is going to be much, much smaller. So the idea is we only have labels for very few data points, and the rest are unlabeled. So the problem we want to ask is, okay, how do we extend these known labels onto the rest of the data set? So the sort of classical way of looking at this is to say, well, let's just ignore the unlabeled data points and let's just look at the labeled data points, and let's do something like minimize this Dirichlet energy subject to taking the constraints. Okay, so what I want to motivate now is, okay, we can get a much better solution if instead we try and include the unlabeled data points. So in particular, when we throw away the unlabeled data points, what we're doing is we're throwing away sort of information we have about the geometry of the problem. So let's consider this sort of toy example. So if I give you two data points, a red data point and a blue data point, and I say, let's partition the space, well, there's only really one thing we can do, and that's draw a line down the middle, and anything on this side is red, anything on this side is blue. Now, if I give you some unlabeled data points, okay, so something like this, okay, if I apply my classification rule, okay, you can kind of see it doesn't give what we'd think of as being a good fit. Okay, what is much better is if we move this line here over into this sort of big gap here, and this would be our sort of a much better solution. Okay, so to emphasize what the unlabeled data points are doing is they're informing us about the geometry, so we somehow have a better classifier. Okay, so how to sort of do this in a sort of rigorous framework. So we will use the random geometric graph model. So okay, so in this model, our data set xi from 1 to n, these become the nodes of a graph. Between each pair of nodes, we put an edge, and we weight this edge according to some function eta epsilon. So I'll kind of return to this epsilon later, but this is a length scale. Okay, but the important part at the moment is that the weight of this graph depends on the distance between the edges. And the sort of typical example to have in mind is when this sort of eta x is 1 if x is less than 1 and 0 otherwise. So what this means is that our weights are only going to be positive if they're closer than epsilon, and they'll be 0 if we're further than epsilon. Okay, so this is just sort of an example. The theory is more general, but this is the sort of thing to have it in mind. Okay, what we do then is we throw away edges with 0 weight, and we should be left with a sort of much sparser graph. So, okay, so this sort of says, well, okay, we can't choose epsilon to be too small. So again, thinking back to this example here, if I choose epsilon to be very small, then I will have no edges in my graph, and you can sort of see that in this case we won't really be able to represent the geometry of the problem. Okay, and it's a result by Matthew Penrose. He can tell you exactly how this epsilon should be related to the number of data points you have if your data points are IID from some measure mu. So, okay, so what he says is that the connectivity radius, so this would be the smallest epsilon such that the graph is connected, should scale as at least log n over n to the dth root. Okay, so again, this should be sort of natural that if our data points were all uniformly separated, then of course it should be square root of d to the 1 over n, and then the randomness introduces this sort of extra log n term. Okay, so this kind of says we can't choose epsilon to be too small. Let me say now, okay, why we shouldn't want to choose epsilon to be too big either. So let's consider sort of this toy data set. So this is the two spirals data sets. You see we have sort of two spirals going around each other. And here, you might not be able to see, but there are two labeled data points. So there's a yellow point there, and there is a dark blue point there. And what I want to do now is label this data set. So here, I choose my epsilon to be quite large. So now you can see that so I've only plotted here the edges which are positive. So you can see there's quite a few edges between these two spirals. So when I apply my sort of off-the-shelf graph cut algorithm, what I can see is that I don't really pick out these spirals, right? So I mean, like this here is being grouped with this part here, and then everything else is labeled yellow. So this somehow isn't very good. We'd like to pick up the geometry of the problem. If I choose my epsilon to be much smaller, now there's very few edges between these two spirals, and you can see we do a much better job. So other than maybe these few points here, everything seems to be sort of in the right class. So, okay, so epsilon also shouldn't be too big. At least I'm trying to motivate, we want to take epsilon off to 0, and that really sort of really will capture our geometry in the sort of large data limits. Okay, so we recall this is our problem. This is the classical approach. So what's the approach we take in this talk? So we look at the P Laplacian regularization method. So this was proposed by Zugar, Armani, and Lafferty, and Zuna and Schlockhoff. And the idea is we want to minimize this functional En. So the idea is that this functional here is really resembling this Dirichlet energy. But okay, I mean I've changed the 2 here for a P here. And now I'm using finite differences rather than derivative. But because I'm working on the level of the graph, then I really have the data is informing okay, what would be sort of have low energies. So in particular, what we're saying is that, so if we're looking at minimizing this functional here, if this is small, well, okay, it implies that Fn of xi has to be close to Fn of xj whenever wij is large. Okay, so something being closer on the graph means that we should have sort of similar labels. So we're moving away from sort of Euclidean geometry onto geometry on the graph. Okay, so the variational problem we're going to consider is to minimize this energy over all functions from xn to r, subject to taking the constraints that Fn of xi is equal to yi for all I in our constraint set. Okay, so let me sort of give like a toy calculation which says what we should expect in the limit. So again, we assume that xi is IID from some measure mu, and mu has density rho. So let's start off with our discrete energy. So okay, so here all I do is I substitute in my definition for the weights. So wij was equal to 1 over epsilon to the d times eta xi minus xj over epsilon n. And I've changed nothing else. Okay, so if we're thinking when n is very, very large, then I replace these summations with an integral, and I'm integrating with respect to the measure mu, which has density rho. Okay, so formally at least you can see that these 2 things here should be close. Okay, I do nothing but a change of variables, this line to this line, so I just let z be equal to x minus epsilon n, and okay, this is what one gets. Okay, now if I look at sort of this term here, okay, and this term here, what I have is a finite difference, and I'm dividing through by something which should be on the on the order of the difference itself. So one sort of expects that this difference here divided by epsilon is going to be the derivative in the direction z. Okay, and if we also assume that rho has some sort of continuity, then rho of y plus epsilon z should be approximately equal to rho of y, and I end up with a function that looks like this. Now I can play a little sort of game, and I can sort of take advantage of the isotropy in eta, and I end up being able to take one of these integrals out as a constant, and so what I end up with is an energy that looks like this. So this now, of course, is very similar to the sort of classical case which I showed before. The only difference being is now I have this rho squared here. So our data is now represented in terms of this density. And see here. So this now defines my continuum energy. And what I want to know is, when do constrained minimizers of ENP converge to constrained minimizers of E infinity P? Okay, so immediately, if we think about imposing pointwise constraints, then we know that for this to be sort of a well-defined model, we have to have P being bigger than the dimension of the space. Here, when P is bigger than the dimension of the space, we have continuity, so we can define pointwise evaluation. If P is less than or equal to D, then this makes no sense. So immediately we can say, well, P greater than D must be necessary for the constraints to be respected. Okay, and then the natural question is this all we need? The answer to that is no. Okay, so I just want to emphasize this is where the number of constraints is going to be fixed. So this capital N is finite, and we're taking this little n off to infinity. Okay, so why is this condition at P greater than D not enough? Well, the problem is when we have spikes. So if we consider the function, if we consider the spike at the first data point, so this is Fn of x1 is equal to 1, and Fn of xi is equal to 0 for all I greater than or equal to 2. If this has low energy, then this is bad. It means we can put a spike at the first data point, okay, and then if we're not paying anything in the limits, then of course we expect that we can do this for all the constraints, and there's nothing wrong with replacing this one with a yi. Okay, so let's look at the energy of this spike. So if I just substitute in, this is what I get. Okay, if I think now what my sort of example eta is, so I think of eta as being just 1 when the argument is less than 1 and 0 otherwise, then this summation here is just counting the number of data points in a ball at size epsilon around x1. Okay, so this is in our sort of our prototypical example. So I know how this summation is going to scale. It's going to scale roughly as n times the radius of the ball of the volume of the ball of radius epsilon. So this is n times epsilon n to the d. So this red term here should be an order 1 term. And now if I just look at, okay, what are the other terms I have left over? Well, the important part is this epsilon n to the p times n. So if this epsilon n to the p times n is going to infinity, then this spike is not paying anything in the limit. Okay, so this is kind of bad, right? So, okay, and actually this sort of example, it turns out to really be sort of sharp. So I'll show you a theorem soon, which will sort of make this sort of rigorous, and it will show that if epsilon n to the p times n is going off to infinity, then our problem is ill-posed. So what ill-posed means is that we're losing our constraints in the limit. On the other hand, if epsilon n to the p times n is going to 0, so this will mean the spike is paying a sort of infinite cost, it will actually turn out that our problem is well posed in the sense that minimizers of this ENP Fn are converging to minimizers of the continuum problem, but with the constraints. Okay, so I've kind of glossed over something is that, well, what do I mean by minimizers Fn converging to minimizers of a continuum problem? These Fn's are only defined on the graph. They're not defined outside of it. So what I need is a topology which allows me to compare discrete to continuum. Okay, and so this topology I'm about to describe is actually work of Nicholas Garcia-Trillis, who's in the audience. Okay, so the idea then is to first of all define a space where we can talk about discrete and continuum functions. So the idea was to couple this with the measure. So instead of thinking of Fn as being a discrete function, we think of Fn and mu n, so mu n is the empirical measure, as being a pair. And then in the continuum domain, we have F and mu, again, as a pair. So now we can look at these as being in the same space. So the space is this TLP space, which is the couplings of functions, which are LP integral with respect to mu, and probability measures mu in P of x. Okay, so this now means that our discrete sequences and our continuum sequences are in the same space. Okay, so we can define a metric on this space. So the metric we give is that, that Nicholas gives, is that we should, okay, so that we, how should I say this? So what we want to do is we want to sort of look at transport maps between mu and nu. So this is just a way of sort of rearranging the measure mu onto the measure nu. So the first thing we want to say is that we don't want this rearrangement to be sort of too far. So it should penalize moving too far. Moving this mass from one part to too far away in the domain. So this is where we penalize this sort of these transport maps x minus tx to p. And then secondly, we want to penalize the difference of f with the difference of g after it's being rearranged. So what in our context we think of this T as really being like a partition of the space. So what this is doing is it's dividing our space up into regions, and then we map each region onto one of our data points. So so here g would be our discrete function, but after we composed it with T, then it's defined on the whole domain. Okay, so this of course is very similar to a Wasserstein distance. And the Wasserstein distance one only has sort of the first term here. And I mean there are sort of more connections between these two metrics. Actually, a lot of the properties, such as proving that this is a metric, follows directly from the fact that the Wasserstein distance is a metric. Okay, so this is sort of the the sort of metric way of looking at things. In terms of actually how we implement this is in terms of this proposition. So if we assume that mu is absolutely continuous, then Fn mu n converging to F mu in TLP is equivalent to saying that mu n converges weak star to mu. So in our context, this mu n is going to be an empirical measure, which with probability 1 will converge weak star. And saying that there exists a sequence of transport maps Tn of x going Tn going from x to x, such that Tn pushes forwards mu into mu n, and Tn is converging to identity in LP, and that Fn composed of Tn is converging to F in LP. So again, we think of this as being, so Fn is our discrete function, Tn is our partitioning of our space, and all we're saying is that after we raise Tn to the whole domain, that this is converging to F in LP. So this is why it's called TLP, right? Because we transport and then we compare in LP. Okay, so this is the topology. There's sort of one more sort of ingredient we need in our proofs, and this is how to analyze sequences of variational problems. So, okay, so we do this in the gamma convergence framework. So maybe some people already know gamma convergence, maybe some people don't. For those that don't, there's kind of a nice sort of picture about how to sort of understand it. So let's say we're given a sequence of variational problems. So this would be like the blue curve and the green curve. So there's the green curve, which is kind of oscillating a bit slower, and then the blue curve is oscillating much faster. And what we're interested in is, are minimizers and the minimum of these sequence of functionals, are they converging? So I think whenever you're given like a sequence of functionals, maybe the first thing to ask is there a strong limit? So of course there isn't a strong limit because we have oscillations. And the second thing to ask is, well, maybe there's a weak limit. Okay, I mean, yes, there's a weak limit, right? We just cancel out the oscillations, and the weak limit is this red curve here. But of course, if we're interested in the minimizer and the minimum, then the minimizer and the minimum are going to be over here, whereas the minimizer and the minimum of the weak limit are over here. So this isn't the right topology to consider. Okay, the right topology to consider is the gamma convergence, is the gamma limit. So the gamma limit is this black curve here, which is the sort of limiting lower semi-continuous envelope of the functional. Okay, so now you can see, okay, the minimizer and the minimum is over here. Okay, there is a definition for gamma convergence, which really just says, okay, it's the black curve. There is a theorem which says that if, assuming that sequence of minimizers are pre-compact and we have a gamma convergence result, then this picture holds. So the minimum of the gamma limit is equal to the limit of the minimum of the sequence of functionals, and any if we take any converging subsequence of these fn's, then it's going to converge to a minimizer of the continuum problem. So this is really just convergence of the minimum and convergence of minimizers. Okay, so kind of armed with these sort of background results, we can state this first theorem. Okay, so we let p be greater than 1. We assume epsilon satisfies the lower bound to ensure connectivity of the graph, and we let fn be a sequence of minimizers of our graph energy, satisfying the constraints, where Zn is now just the first capital N. Okay, 1 to capital N. Then we have with probability 1 that Fn is converging in this topology TLP, okay, along subsequences to some F in the subtle space W1P. Okay, now we break the theorem up into two cases, the ill-posed case and the well-posed case. So in the well-posed regime, we assume that n times epsilon n to the p is converging to 0 as n goes off to infinity. So this implies a upper bound on epsilon. Okay, then we can strengthen this result here with the following. So in fact, the whole sequence Fn converges, not just subsequences. And it's not converging, well, it's converging in TLP, but it's also converging locally uniformly. So a much stronger sense of convergence. So what I mean by locally uniform is that up to maybe the boundary of x, we have that the maximum of f of x minus fn of x is converging to 0. Okay, so this is the continuum functional restricted to the graph. Okay, and then this is the function on the graph. Okay, and this convergence here is now strong enough that we can pass through the constraints to the limit. So we have that this limit here, f, is going to be a minimizer of infinity subject to the same constraints. Okay, on the other hand, we have the ill-posed regime. That's if n times epsilon to the p is going to infinity. As n goes to infinity, then in fact f is going to be a constant. So in particular, it's not going to respect the constraints. So all the constraints now have disappeared in the limit. Okay, and so we can see this in sort of toy examples. So let's consider sort of a 2D problem where so my data points now are distributed on this sort of plane here, and they're just uniformly distributed. I choose my epsilon to be 0.06, so this is quite small. And then I have two constraints. So one of my constraints is down here, so I force to take the value 0. And one of my constraints is up here, where I force to take the value 1. Okay, and then I just compute my minimizer when p equals 4. So because I'm in 2 dimensions, I must have p being strictly greater than 2. So I just chose p being equal to 4. Okay, and this is the continuum problem. And you can kind of see, so here I just plot the grid here is just for visualization. You can kind of see, okay, this is quite close. We're not doing too bad a job. Okay, so what happens if I play around with my epsilon? So let's zoom in around this point here and see what happens as I adjust epsilon. So this is for epsilon 0.05, roughly the same epsilon as I had in the previous slide. And you can see actually we do have like a very small spike around this. So this is our training data point. Okay, but the spike's small. As I increase my epsilon, this spike here gets bigger. Okay, as I increase epsilon further, my spike gets even bigger still. So this is really saying, okay, what our theorem says, that as epsilon gets bigger, our problem's becoming ill-posed, right? These spikes here are paying less and less, they're becoming cheaper and cheaper. So okay, so we're losing the effect of the data. Okay, so just like an idea of how the proof works. So I mean, it's kind of natural to say that this discrete energy should be like the continuum energy, but in fact that's not quite true. What actually happens is that this discrete energy is like the continuum energy after it's been sort of modified on the scale of epsilon. Okay, so what this means is that the graph construction actually really kind of has this sort of smoothing effect. Okay, so let me just explain. So this Fn tilde is Fn after it's been raised to the continuum domain. So we have some transport map Tn, which we use to extend our discrete function to our domain. And then this J epsilon n is just some modifier, but it's okay on the scale of epsilon. So what this kind of means is that now if we wanted to just control the regularity of Fn, then actually we can't really, so we'd like to control the regularity of Fn tilde, but in fact we can't really do that. We can only really control the regularity of Fn tilde after it's been modified by J. So if we're thinking about Fn being a sequence of minimizers, then this sequence in n here is going to be bounded. So it means this sequence here is going to be bounded, but this doesn't apply any sort of compactness directly. So to deal with this, we have to control the oscillations of Fn on the scale of epsilon. So, okay, so we define what it means for an oscillation on the scale of epsilon. This just means we take the maximum of a ball around a certain data point of radius epsilon, and then we subtract the minimum on the same ball. Okay, so this is the maximum value that the function can take and the minimum value the function can take. A little bit of algebra will reveal that this oscillation can be bounded by n times epsilon into the p times the energy of the function onto the pth root. So again, thinking in terms of minimizers, then this term here is going to be bounded. So what happens to asymptotically really is determined by n times epsilon n to the p. And this is where it shows up in our proof. Okay, so now we use Sobolev embeddings of this J epsilon n, modifying Fn tilde. So this gives us L infinity, well, it gives us like C0 alpha convergence of this sequence here. And then we can use that plus this control of oscillations to get convergence of an L infinity-like convergence of this discrete problem to the continuum problem. Okay, and now we just add a gamma convergence result of ENP to E infinity P plus a TLP compactness result. Actually, this is really due to Nicholas and some of his previous work. And this gives us the convergence of the constraints minimizers. Okay, so really the reason why our method didn't work for p being less than or equal to d is because we always fix the number of constraints. So the question is, okay, what happens if we get more constraints? Can we go below p being less than or equal to d? And of course the answer will be yes. Okay, so particularly we're interested in how can we get a well-posed result when p equals 2. So p equals 2 is somehow the most important regime because it's the easiest one to do numerically. Okay, so there's closed form solutions when p equals 2, right, which makes it very kind of desirable. Okay, so one approach of this is to increase the weights around the labeled data points. Okay, and this somehow gives you more regularity at the labeled points, so that you can, so you still have sort of, I'll say it's like local continuity, or you can think of it as, you can still make pointwise evaluation at the limit. So this is an approach taken by Jeff Calder and Dan Slepchev. It's not the approach we're going to take here. Okay, so the approach we take here is we're going to assume that we can take more and more training data points, and the question we're going to ask is, well, how big does this set have to be? Okay, so I want to recall that we have our training data points. These are xi and yi. Xi lived in some Euclidean space. Yi is our labels. Okay, now we will assume that the probability of a data point being in a set Zn is equal to beta n. So I index beta with n so that I can take this off to 0 still. So it means we're still working with an asymptotically small size of the data. So an asymptotically small proportion of the data is labeled. Okay, so it's really still the semi-supervised learning problem. Okay, if our data point is a training data point, then we set yi to be equal to g dagger xi for some g dagger which we fix. So the well-posed case would be when minimizers of this energy subject to the constraints converge to g dagger. The ill-posed case would be when minimizers of this EMP subject to the constraints are converging to a constant. Okay, so the question is, okay, which case will be in? How does beta need to scale? How does epsilon need to scale? Okay, so let me first give the ill-posed regime. Okay, so p greater than 1, epsilon satisfies the same lower bound due to the graph connectivity. And we're considering Fn, which is a sequence of minimizers of the EMP subject to the constraints. If we assume that beta n, so the probability of a training data point, the probability of a data point being in our training set is scaling much less than epsilon n to the p. And okay, I think this is a technical, this is, okay, we do need this. Okay, we also have to have this sort of additional lower bound and epsilon n. Okay, then almost surely Fn is going to be pre-compact, so we already knew this. But what we know now is that the convergent subsequence is converging to a constant. So this says, okay, if the portion of my training data points is small, and this is what it means by being small, then I don't see my data in the limit. And the proof is really the same as the proof from right at the very start, where we just put spikes at each of these training data points, and then we just compute the cost, and we work out that actually this is still asymptotically sort of optimal. Okay, so the well-posed regime, so we only have a proof when p equals 2. Okay, again, epsilon satisfies the same lower bound. Fn is a sequence of minimizers, satisfying the constraints. Now we assume that, okay, the inverse inequality, so p here is 2, but I just left it as p, so you can see that this is the same bound. We do need this extra lower bound here as well. So if epsilon is sort of sufficiently large, actually this term here dominates. It's only when epsilon is very close to the connectivity regime that this actually plays a role. Okay, but assuming these two sort of bounds hold, then we probability 1 Fn is converging to d dagger uniformly. Okay, so i.e. we have this. Okay, this is the same convergence I had before, but actually now we have like uniform of the whole set, not just locally uniform. Okay, so how much time have I got, by the way? Okay, oh great, okay, so I probably won't need all of that, so I think I'm quite close. Okay, so let me just sort of give some description on how this proof works for p equals 2, and why it works for p equals 2 and not for other choices of p. So the idea we use is that we have this random walk interpretation of minimizers. So we have our graph Gn, so this is the graph with our xn when our edge weights are w. We then take this random walk, so ztx is the random walk starting from the point x, some part of our graph, and transitions with the probability. Okay, so if we go from xl to xk, we're probability proportional to wkl. Okay, so if we again think about our prototypical example, all we're doing is we're choosing at random a point. So if we start off at xl, we choose a point randomly within the ball of size epsilon, and then we jump to that point at the next step. Okay, we define the stopping time as being the first time that this random walk hits a constraint. Okay, so we start at some point x, we wander around in our graph, at some point we'll hit a constraint, at that point we stop the random walk. Okay, it turns out that if one defines Fn to be the expected value of g dagger when this random walk stops, then Fn is a minimizer of this 2 Dirichlet energy subject to the constraints. Okay, actually the proof is very simple. It just sort of one really just sort of differentiates this and shows that the properties property holds. Okay, so now we can kind of control this sort of random walk, and this will give us our sort of our convergence result. So the first thing we do is we show that this random walk, okay, the stopping time is greater than k with probability that's quite small. Okay, and this happens with probability, okay, which is quite large. Okay, so I want to be quite clear about this. This probability itself depends on the graph. The graph is itself a random variable, so we have two probabilities kind of in play. So we have the probability of the graph. So what this means is that the data set that I'm given isn't really pathological. Okay, so then, but assuming that the data set I'm given is kind of sufficiently nice, then we can bound the probability that the random walk stops before time k as being some sort of exponential to the minus k times beta n. Okay, the next thing we do is we control how far the random walk is going to move. This, of course, so this bound here should be sort of very natural because, of course, if we're doing this in the continuum domain, then we're expecting the random walk to move with sort of length scale, square root of k, where k is the number of steps you make. Okay, so k is the number of steps we make, so our sort of bound is of the order epsilon n times the square root of k. So this is quite natural. We have slight complications because we're on a graph, and there's sort of there are sort of biases that our data isn't uniform distributed, but still one kind of expects this. And again, we have this bound that we're moving, okay, with this sort of going to this, okay, with high probability. So combining these two results here, we can say that the stopping time of the random walk is going to be, that the difference between the random walk from where it ended up and where it started, okay, is less than some alpha with probability, okay, 1 minus some constant, e times minus some constant, alpha is going to beta n over epsilon n. Okay, and this now is why we need this term here to be going to infinity. Okay, if G dagger is Lipschitz, then we can transfer this bound here onto an L infinity bound between Fn and G dagger. Okay, so what we get is that this bound here holds, and this is for all alpha greater than 0. If one chooses alpha optimally, we get up to logarithmic terms that this is going to be order epsilon n over square root of beta m. So actually, the result I had in the previous slide, one can add a rate to that. Okay, and this is the rate. Okay, and that's actually the rest of my talk. So thank you very much.
I have a question regarding the results, the second result for p equal 2.
Yeah.
So I didn't get, but probably I was too slow, where p equal to 2 enter? I mean, in the end, it's a capacity question, right? I mean,
okay. So this, of course, okay. So it's a capacity question if you want to answer this sort of, I guess, in more generality. So the p equals 2 entered because we have this random walk interpretation, and this interpretation is only valid for p equals 2. So it doesn't hold for any other p. But okay, you're right. I mean, this is really the rates depend on the capacity. We've tried to prove this using the capacity of points. It's actually very difficult to do. So I mean, a lot of these sort of usual. So we haven't really tried doing this using sort of PDE methods, which maybe PDE methods typically don't give you. They don't let you go down to like the smaller sort of epsilon. You have to have a sort of larger bound, which is kind of needed for the pointwise convergence of these Laplacian operators. But that might be the right way to do it for, you're not optimal for small epsilon, but you do okay for larger epsilon. There are sort of variational ways to prove the capacity of, this is like the perforated domain problem. So of course, there are proofs that use gamma convergence, but the only proof for this I know really uses symmetry of the problem, and in this problem, it's not clear how this would. Well, it's not clear how to apply these proofs to this thing here. But I mean, I'm open to suggestions if you think of a way to do it. Yeah.
So I guess p equals 2 is equivalent to the electric model approach, where you put voltages across the labelled points and then use Kirchhoff's law to update the unlabelled points as they arrived. And I think the solution that you get from that is the same as this. Is that right?
I think that's right, but I have to admit I don't really know very much about that. I think it's in one of the, I think that's what you just said. It might be in the Zulafty and Garamani paper, that connection there. I honestly don't really know it.
So there was some work by Amazon researchers last year where they used that to develop a streaming model. I mean, the analysis that they're developing a practical way to do semi-supervised.
Okay, yeah, I'd be interested to get
I think it's equivalent.
Yeah, I honestly, I don't know. But I'm interested to know.
Do you result into the situation in which the underlying measure is singular? Like, for example, the data that is plotted by a small dimensional.
One can do this on a manifold as well. Well, we didn't do it on a manifold, okay, but Nicholas has results for most of the preliminary results which we need, and these all hold on manifolds as well. There is an assumption that this density is always banded above and below, but if this density, okay, is a density on a manifold, then this is sort of fine. I mean, if you're thinking about putting Diracs at certain points, then this we probably can't do, but well, we can't do yet, but maybe.
All right, there's no more questions. Let's thank Matthew once again.